Welcome to this comprehensive guide on handling latency and interpolation, crucial concepts for developing smooth and responsive multiplayer games, especially for beginners. We will explore these fundamental aspects in detail, providing practical insights and demonstrations within Visual Studio and Unity 3D to help you build more robust and engaging gaming experiences. In multiplayer gaming, latency refers to the delay between a player's action and the server's response, or between the server's update and a client's display. This delay, often measured in milliseconds, can significantly impact the player's perception of the game, making actions feel sluggish or out of sync. High latency can lead to a laggy experience, where player actions feel unresponsive and game states appear out of sync across different clients. This can manifest as characters teleporting, shots not registering, or other frustrating visual discrepancies that detract from the overall gameplay. Interpolation, on the other hand, is a technique used to smooth out the visual representation of objects moving between discrete network updates. It bridges the gaps between received data packets, creating a fluid and continuous motion that masks the inherent choppiness of network communication. Without interpolation, objects would appear to teleport or jump abruptly as new data arrives, creating a jarring visual experience for players. This sudden, discontinuous movement can be highly disorienting and make it difficult for players to accurately track and interact with game elements. Our goal is to minimize the perceived impact of latency and use interpolation effectively to create a seamless and enjoyable gameplay experience. By understanding and implementing these techniques, you can significantly enhance the responsiveness and visual fidelity of your multiplayer games, leading to greater player satisfaction. Let's begin by understanding how to simulate latency in a controlled environment, which is crucial for testing and debugging network code. Simulating latency allows developers to proactively identify and address potential issues that might arise under real-world network conditions, ensuring a more stable game. In Unity 3D, you can simulate network latency using various tools or by implementing a simple delay mechanism within your network manager script. This controlled simulation provides a safe sandbox to experiment with different latency values and observe their effects on your game's behavior without relying on an actual high-latency connection. For instance, you can add a thread, sleep call, or use a coroutine to introduce an artificial delay before processing incoming network messages. This programmatic approach allows for precise control over the simulated delay, enabling you to test specific latency scenarios and fine-tune your network synchronization strategies. This allows you to observe how your game behaves under different network conditions without needing an actual high-latency connection. By systematically testing with simulated latency, you can identify bottlenecks, optimize your network code, and ensure your game remains playable and enjoyable even when network conditions are less than ideal. Next, we'll delve into client-side prediction, a powerful technique to mask latency by immediately executing player actions on the client. This method significantly improves the perceived responsiveness of the game, making it feel much more immediate and fluid for the player. When a player presses a key, their character moves instantly on their screen, even before the server acknowledges the action. This immediate feedback creates a sense of direct control, reducing the frustrating delay that can occur in high-latency environments. The server then validates this action and sends back the authoritative state. If there's a discrepancy, the client reconciles its state with the server's. This reconciliation process ensures that while the client provides immediate feedback, the server ultimately maintains control over the true game state, preventing cheating and maintaining consistency. Implementing client-side prediction involves storing a history of player inputs and states on the client. This historical data is crucial for the reconciliation process, allowing the client to accurately resimulate actions if a server correction is received. Upon receiving a server update, the client rolls back its state to the time of the server's update, reapplies any unacknowledged inputs, and then updates its visual representation. This rollback and resimulation process ensures that the client's view eventually aligns with the server's authoritative state, even after initial prediction. This technique significantly improves the perceived responsiveness of the game, making it feel much smoother for the player. By providing instant feedback and intelligently correcting discrepancies, Client-side prediction creates a more immersive and less frustrating experience, especially in fast-paced multiplayer titles. Now, let's explore server reconciliation, which works hand in hand with client-side prediction to maintain game state integrity. Server reconciliation is the server's mechanism for ensuring that all clients eventually agree on the true state of the game world. The server is the ultimate authority for the game state. It receives client inputs, processes them, and determines the true outcome of actions. This centralized authority is essential for preventing conflicts and ensuring fairness across all connected players. When a client's predicted state deviates from the server's authoritative state, the server sends a correction. This correction informs the client of the true game state, prompting it to adjust its local simulation to match the server's reality. The client then adjusts its local simulation to match the server's, often by rolling back and replaying inputs from the point of divergence. This ensures that any temporary visual discrepancies caused by client-side prediction are quickly resolved, bringing the client's view back into alignment with the server's authoritative state. This ensures that all players eventually see the same game state, preventing cheating and maintaining fairness. Server reconciliation is a critical component in competitive multiplayer games, as it guarantees that no player can gain an unfair advantage through network manipulation or client-side exploits. Next, we turn our attention to interpolation, a technique vital for visually smoothing out movement between server updates. While client-side prediction handles immediate input, interpolation focuses on making the movement of other players and objects appear fluid and natural. Instead of instantly snapping to a new position received from the server, interpolation gradually moves an object from its last known position to its new target position. This gradual transition creates a visually pleasing effect, masking the discrete nature of network updates. This creates the illusion of continuous motion, even though updates are discrete and arrive at intervals. By smoothly blending between known states, interpolation prevents the jerky, teleporting movements that would otherwise occur, making the game world feel more alive and responsive. In Unity, you can implement interpolation by storing the last two received positions and timestamps for each networked object. These data points provide the necessary information to calculate the intermediate positions for smooth visual transitions. Then, in the update or fixed update method, you can use vector3.lerp or quaternion slurp to smoothly transition the object's transform. These functions allow you to linearly interpolate between two positions or spherically interpolate between two rotations, respectively, over a specified duration. A common approach is to interpolate based on a fixed historical buffer, typically 100 to 200 milliseconds behind the current time. This buffer ensures that the client always has a small window of past data to work with, allowing for consistent and smooth interpolation even if network updates are slightly irregular. This buffer ensures that the client always has two valid data points to interpolate between, even if network updates are slightly delayed. By maintaining this buffer, the interpolation system can gracefully handle minor network fluctuations without causing visual hitches or stuttering. Let's move on to extrapolation, a technique used when interpolation isn't possible, such as when a new network update hasn't arrived yet. Extrapolation attempts to predict future positions when there's a temporary lack of incoming data. Extrapolation attempts to predict an object's future position based on its last known velocity and direction. By continuing the object's movement trajectory, it can maintain the illusion of continuous motion during brief periods of packet loss or delayed updates. While it can provide a smoother experience during brief network hiccups, it carries the risk of overshooting or predicting incorrectly. If the actual movement deviates significantly from the prediction, the object might visibly snap back to its correct position once new data arrives, which can be jarring. Therefore, extrapolation should be used cautiously and typically for short durations, reverting to interpolation as soon as new data arise. It's a valuable tool for masking very short network interruptions, but its inherent inaccuracy means it should not be relied upon for extended periods. In Unity, you might implement extrapolation by continuing to apply the last known velocity to an object's position if no new network data has been received within a certain time frame. This can be done by storing the object's velocity and applying it in the update loop until a new network update provides authoritative position data. This can be a good fallback for very brief periods of packet loss or high jitter, preventing objects from freezing entirely. By keeping objects moving, even if slightly inaccurately, extrapolation helps maintain the flow of the game and reduces the perceived impact of minor network issues. Finally, let's discuss some advanced considerations and practical tips for optimizing your network code. These strategies go beyond the basics and can further refine the performance and reliability of your multiplayer games networking. Prioritize sending critical data more frequently, such as player positions and actions, while less critical data can be sent less often. This bandwidth optimization ensures that essential game information is always up to date, while reducing unnecessary network traffic for less time-sensitive elements. Use delta compression to send only the changes in an object state, rather than the entire state, reducing bandwidth usage. Instead of transmitting a full snapshot of an object, delta compression sends only the differences from the last known state, significantly cutting down on data transfer. Consider using a fixed update rate for your physics and network simulation, decoupling it from the client's rendering frame rate. This ensures consistent simulation results across all clients, regardless of their hardware performance, leading to a more predictable and fair game environment. This ensures consistent simulation results across all clients, regardless of their hardware performance. By separating the simulation logic from the rendering, you can prevent frame rate drops on one client from affecting the game state or synchronization for others. Implement a robust system for handling packet loss, such as reliable UDP or custom acknowledgement mechanisms, to ensure important data reaches its destination. While UDP is fast, it's unreliable. Adding a layer of reliability ensures that critical game data, like player commands or health updates, is guaranteed to arrive. Regularly profile your network performance in Unity's profiler to identify bottlenecks and areas for optimization. The profiler provides invaluable insights into network traffic, processing times, and potential performance issues, allowing you to pinpoint and address inefficiencies in your network code. By applying these techniques, you can significantly improve the network stability and responsiveness of your multiplayer games. Mastering these concepts will enable you to create a truly seamless and engaging experience for your players, even across varying network conditions. Mastering latency and interpolation is key to delivering a professional and enjoyable experience for your players. These fundamental networking principles are essential for any developer aiming to create high-quality, competitive, or cooperative multiplayer games that stand out. Thank you for watching this guide. We hope these insights help you build more robust and engaging multiplayer games. Remember, continuous learning and experimentation are key to excelling in game development, especially in the complex world of network synchronization.